Hi there and welcome to this video for Senior Physics on Light and Waves. In this video we're going to look at wave refraction. So basically wave refraction occurs when a wave moves from in water through different areas of depth, either from deep to shallow or shallow to deep. Now the key thing to understand is that as it moves from a deep water area to a shallow area, the wave speed is going to be altered. And this is altered due to the friction which is generated between the seabed and the water itself. In deep water, what you tend to find is that the water is free to move. There's very little friction. Because there's very little friction, the wave is unaltered, so it goes at its fastest speed. However, when it approaches things like the shore or a sandbank, the depth of the water decreases. That means there's more interaction between the water and the seabed, so more friction. With more friction, you slow down the speed. Because you slow the speed, it has the effect of changing the direction that the wave is moving in. Now, when we look at wave refraction, especially with water waves, the laws of refraction that we learned earlier in the light units still apply, which means that as the wave is slowed down, which is basically what we had with that denser medium, the result is that the angle of refraction moves towards the normal or to the normal. However, when you start going into a deeper area, it's like going into a less dense medium, and as a result, the wave speed increases, which means that the angle of refraction moves away from the normal. Generally, we tend to deal with situations when we're talking about water waves where we're always going from deep to shallow, because let's face it, the waves are generated out at sea and come close to the beach. The only way that you would have anything really in the water going from shallow to deep, or waves going from shallow to deep, is if you were you have water going over maybe a sandbar, and as a result, as it goes over the sandbar, it then goes into a deeper area, and that will alter the position of the waves. So let's have a look at what happens when we encompass these two phenomena. So the first one we're going to look at is when we go from deep to shallow. This is the most common thing that you'll see, and this sort of explains the reason why if you look at a wave coming up the beach, it actually comes up the beach even though that the waves out to sea may be moving at a totally different angle. So let's look at the diagram that we've got here. In the white area, we're talking about deep, and in the shallow area, we're looking at the blue area. Now what's happening is the waves are coming in at a long wavelength, so this is a constant wave speed. This will be the fastest wave speed that the waves will be travelling at. Then they come across this shallow area. Now the shallow area basically could be approaching a beach or a landfall, continental shelf, whatever you want to look at. But the key thing to understand is that the depth of the water is going to decrease. That's going to increase the amount of friction that's going to generate. Now what happens is as each wave approaches it, part of that wavefront is actually going to begin to slow down. And you can see if you look at the very first line that encounters the blue wave on the far left hand side, you can see that it bends. Now what's happening is as that wavefront, especially the one down here, as it enters that shallow area, it slows down. The rest of the wave is travelling still fast. So the result is the wavefront begins to bend as it is pulled round due to the friction which is generated between the boundary of the deep water here and the seabed here. The result is that the wavelength is actually going to start decreasing, and you will see that the wavelength will be, it gets a lot shorter. The frequency should be the same because what's happening there is the wave speed has decreased. So let's draw a refraction angle diagram like we're used to. So here I've got the incident wave coming in from the left hand side at an angle theta right. So that's my incident ray coming in on my incident wave. Now it leaves by theta r, and you'll notice that the angle there is closer to the normal. So as a result, this is our diagram which we can generate by simply using arrows to show the wavefronts or the direction of the wavefronts. We get a simple refraction diagram which we can utilize. So we know basically that as we go from deep to shallow, the wave speed will decrease, the angle to the normal decreases, as in it gets closer to the normal. And we also see that the wavelength decreases as the wavefront slow. But remember that the frequency will remain constant because the decrease in wavelength is directly related to the change in speed. Okay? If the change in speed, if it slows down, because it's slowing down, you'll get the same number of waves per second. And as a result, what we notice is that the wavefront seems to bend and come up the beach, even though out to sea it's coming at an angle. Now you can see this in more detail on this diagram here. You can see the waves beginning to bend as they approach the seashore. That's basically because each wavefront is hitting that seabed at a specific angle. As it hits a specific angle, it begins to slow down. The rest of the wavefront is still going at normal speed. So because it's going at a normal speed, it's going faster, so it almost looks to overshoot. So it's almost pivoted at the seabed, and as a result, it curves round as it goes up that seabed. Here's an example in reality where you can see that out to the back on the headland there, you can see the waves are coming in almost straight towards you. However, when it reaches the beach, you can actually see the waves coming straight up the beach. Why is that? They're being bent because of that seashore. Better example, you can see here that those waves are going to come up the seashore basically due to this friction and this changing in speed. Notice that the wavefronts and the wavelengths are comparative. Now they're not going to be a nice straight line obviously because the seabed is going to vary, and everything that you see is going to be a direct result of a contour of the seabed as well. Here's another example that you can see as it's coming up the seabed with the waves going out to sea at a different angle. And you can actually see, which is quite nice here, that light blue area will be your shallow area, the dark blue area is going to be your deep area. So you can see why we're getting these waves forming in this area, in this light blue area, simply because we've got friction which have been generated. Okay, so what happens if we go in the opposite direction? Well, in the opposite direction, where we go from shallow to deep, as I said, maybe coming across the sandbar and going back out into deep water, we'll get a normal incident ray coming in, as you can see there. But what will happen as it goes to deep, it speeds up, and as a result, the wavefronts get further apart. They're also going faster. Again, the frequency will be constant because the change in wavelength will be directly related to the change in speed, and as a result, the frequency will remain constant. So the wave speed increases, the angle to the normal increases for theta r, so for your refractive angle, and we know that the wavelength increases as the wavefronts speed up, but the frequency will remain constant. Okay, well I hope that makes sense. One thing that we do need to remember is that if a wave passes through an object, its speed will always be altered. It doesn't matter whether we're talking about water, whether we're going from air, whether we're going through a brick wall, for example, if we're talking about sound. If it's altered, the frequency generally should stay the same, but the wavelength should change based on the change in the change in speed. There is a slight error there where it says change in the wave frequency. Remember, the wave frequency should stay constant, but the wavelength should change directly related to the wave speed. Also note that if we're going from one medium to another, especially when we're talking about waves, we're more likely to notice that some reflection will occur. And you may have seen that when we looked at things like perspex blocks and we were doing light going through a perspex blocks, you do get some reflection. Now this is also going to follow on from what we talked about with respect to light and heavy springs, where when you've got light springs, waves traveling through a light spring and then going into a heavy spring, if you remember, there is some reflection which comes off where it's inverted and then some of the energy is passed through. So what you will notice is that, for example, if you've got sound hitting a wall, some of that, especially if it's at an angle, some of that sound will be reflected off, but some of it will actually pass through and its wave speed will be altered. That's why you can feel a wall vibrate because of that sound moving through, but you're going to get change in wavelength, and that wavelength in this case will actually get narrower because the speed will actually decrease. Okay, well, I hope I've sort of explained to you this idea of wave refraction. I look forward to you meeting again. Thanks for watching.